So in this video, we're going to be going over another integration method, which is called integration by parts. And integration by parts allows us to basically integrate products. So like, we can be, so if there's two different functions being multiplied, and we want to take the integral of that, the integration by parts actually allows us to do that. So we can just write helps integrate products of different functions. So the general formula for integration by parts is f of x g prime of x so right here, this is basically the product, right? This is a product where there we have f of x as one of the parts, and then g prime of x as the other one. So we're going to be doing integration of parts for definite integrals, so we're just going to add bounds here. So we have two different parts of this integral, right? And they're both being multiplied. And this is going to basically equal f of x times g of x evaluated from a to b. And then we have another part of this setup where we have another integral, but this integral is going to be a lot simpler than what we had here. So the goal of integration of parts is trying to reduce this integral into something simpler. And so whatever this integral is, it needs to be a simpler or more easily integrable than what we had before. So we're going to end up with f prime of x g of x dx. So this is basically a general formula for integration by parts with the terms f of x and g of x. And we have to make sure that f of x and g of x are continuous, and f prime and g prime are also continuous. So what this formula just implies, so let's write that here. This formula implies that f and g, I'm still not going to write the x, just assume that f and g are f of x, g of x. F, g, and f prime and g prime are continuous, and in integration and differentiation, continuity is an important thing, because continuity determines if a function is differentiable, and continuity determines if a function is integrable. So we want to make sure our functions are continuous over the given interval, are continuous over closed interval a, b. We're using closed intervals because these are the intervals include a and b in these upper bounds and lower bounds. So this is the integration by parts formula. But when in order a quick method to actually memorize this formula is using the terms u and v. So what we can do is basically we can switch this formula into a simpler formula that you can memorize. Say if you need to memorize this for an exam, or you're doing this on an exam, you're not going to memorize this entire thing. This can get confusing, right? I just gave you this so you have the general definition of integration by parts. But if you want to memorize this formula, you can substitute u and v. So let's say we set u is equal to f of x, and we say v is equal to g of x. right? Now, what we can do is integrate, not integrate, differentiate both of these functions in terms of x, and we get du is equal to f of x dx. Then right here we have dv is equal to g of x g prime of x dx, f prime of x dx. So we just made the differential. We just made the differentials of each of these functions. And what we can basically do now is we have all of these terms, right? We have all of these terms in the original formula. All we need to do is just plug in. So let's do that. So we know on this side right here, we have f of x and g prime of x, right? And this must be a dx here, from a to b. So what we can just write is so we know u is f of x, so u, and then dv, right? We know dv is equal to g prime of x dx, and we have that right here. Where to go? Dx, so we have that right here, which is going to be equal to, let's see, f of x times g of x evaluated from a to b. So we can write uv, we can just write uv, right? F of x times g of x. U is f of x, v is g of x, minus, we have the integral from a to b of f prime of x and then g of x dx, right? So integral from v du. V is g of x, right? We have g of x right here. And then we have du, which is going to be f prime of x dx, which we have right here. So this is the general formula of that you can use to actually memorize the integration by parts. So let's actually now do like a quick example to show how to actually use this formula. And remember, whenever you have like an integral problem that involves products, it's probably going to be an integration by parts question. So you can use that. You can use the integration by parts for that. And actually, there's one more thing that can get confusing in integration of parts, and that could be determining what are you gonna use as u and what are you gonna use as v. And an easy method to actually determine that is a method called LIATE. So let's write that here. So how to determine what, let's say we're gonna determine what u is. So how to determine what u is going to be, right? So we're gonna use a method called LIATE. LIATE, right? So what this is basically saying, it gives us it goes from left to right, left to right, and it basically shows us priority, which functions are given priority, so we can substitute for u. So the L just means logarithm. So basically logarithmic functions. If you see a log functions like ln x or any kind of log function, we're going to give that priority and substitute that for u. Or if you don't have a logarithmic function, we have the next one. The next step is basically inverse functions. So if you don't have logarithmic functions but we have inverse functions in the product or under the integral, we can substitute u for the inverse functions. And then next is algebraic functions. So say algebraic meaning like x plus 1, something like that. So basic algebraic functions like quadratics and all that kind of stuff. Then we can substitute u for uh, any of those algebraic functions. But remember, the priority starts from this number. The priority is given to logarithmic functions, then to inverse, then to algebraic. Then the fourth, the T stands for trigonometric functions. And then last priority is basically exponential functions. So exponential function is basically e to the 2, e to the x, stuff like that. And you can use this basically process to determine what u is. And this can basically simplify the process when you're actually trying to find the definite integrals. So what all of the stuff I wrote on this page here is very important, and I would recommend writing all this down. And basically it helps you simplify integration by parts while you're doing it. So let's actually go through a quick example. So right here, we have the integral, I stands for integral, from 0 to pi, x squared cosine x dx. So we have this integral. So what we want to do here is basically try to determine, well, what is f of x, what is g of x, what is g prime of x, and what is f prime of x. So first thing we're going to do is actually try to figure out what we can switch around, right? So we know we want the final product to be in terms of this right here. No, in terms of this right here. But we want to rearrange the original integral so it looks something like this, right? So what we see here is that we have an f of x, right? And we have a g prime of x. But in this original function, or this integral, we just have x squared and cosine x, right? So we know we want x squared. So based off of LIATE, we know that we want to give priority to the algebraic functions. Since we only have an algebraic function here and a trigonometric function, the algebraic function gets more priority over trigonometric. So we know that we want u to be x squared, right? And we want cosine x to be basically dv. So we want cosine x dx to be dv. So we need to first determine how can we switch this cosine x into something that looks like this, that looks like g prime of x dx. So that's easy because we know the derivative of sine is cosine, so we can write that here. So we have this, right? We can switch this into 0 to pi. So we know x squared. You can say sine x, the derivative of sine x dx is that. So now we're basically in that form, right? F of x times g prime of x dx, right? G prime of x is this right here. F of x is this right here. So now that we have that, we can use the formula, right? So the formula is basically u dv is equal to u v minus u prime v du. So like that. So we have that right there, right? So first thing first, we already said the algebraic function takes priority over a trigonometric function. So we're gonna set u equal to what was it? X squared. So we're gonna say, well, let's write it right here. U is equal to x squared. Du is equal to 2x dx, right? Then we know that dv, right? This right here. No, dv was basically this right here, cosine x dx. So we know dv is equal to cosine x dx. If you integrate a cosine x, we just get sine x, right? That's what we determine here. So v is equal to sine x. So now we can just plug in for this formula right here. So u times v is going to be x squared times sine x. X squared times sine x minus. The next step is basically the integral of v du, right? So we have v right here, du right here. So it's going to be sine x times 2x dx. So integral of sine x times 2x dx. Now that we've gotten to this part, we do a little simplification, right? So we're basically done with this part right here. We integrated that. That's x squared sine x. Now we just need to integrate this. And remember, this integral needs to be simpler than what we had before, right? We need it to be simpler. So let's see if it is. So x squared sine x minus, and so we can pull out this 2 because of the property of what was it? Definite integrals, where it says that we can pull out constants from the integral sign. So, and I think I forgot the bounds. So bounds were 0 to pi, right? So like that. Now we can pull out the 2, right? So we have the integral 0 to pi of sine x times x dx. So that's what we end up with. And this right here is actually simpler than this. That's because you see there's a power of 2 here for the algebraic function, but over here the algebraic function has a power of basically 1. But the thing is, we have to do integration by parts one more time, since we're still in that form of a product. So let's do integration by parts on one more time. So now, this part of the equation, the expression, we're done. But we still need to integrate this part now. So let's do the same thing we were doing before, right? So let's pull this to the side. So we want to make sure this is in the form, this form right here, right? That we determined before. Let's say like this form right here. So let's do that. We know that we want u to equal f of x. And u is going to be the algebraic function. Since we only have a trig function and algebraic function here, algebraic function takes priority. So in order to basically make this look like this right here, we do x, right? That's f of x times, so the integral of sine x is basically negative cosine x. Yeah, it's negative cosine x. So it's negative cosine x. So what we can do is write negative cosine x prime dx, and we get, now we're in that form, right? Now we can use the integration by parts formula. Let me actually make this a different color. Let's make this blue. So we know the formula says it's going to be u times v, then integral of v du. So we're going to set u is equal to x. U is equal to x. That means that when we integrate, differentiate, du is equal to dx. We know v is going to be, well, what do we have for? We know v is going to be negative cosine x, right here. And we know dv was originally sine x dx. So like that. So what we can do now is just plug in. So uv, so u times v, right here, is gonna be, let's see, x times negative cosine x minus the integral 0 to pi of, so we need v du, so right here, v du, so negative cosine x dx, negative cosine x dx. So this is what we end up with for this integral. And one thing I forgot was basically we need to evaluate this at from 0 to pi as well. But now we have to evaluate this right here from 0 to pi as well. So now the final step would just be putting everything together and evaluating everything from 0 to pi. So let's actually do that. But so we know we're gonna have to substitute this entire expression for this entire expression right here, not including the 2. The 2 is pulled out. So this entire expression. So we're substituting this for this. So let's actually do that right here. Let's pull everything down. So this is going to be x squared sine x 0 to pi minus 2, and then we're going to multiply this by this entire expression we just found. It's going to be negative x cosine x. I just pulled the negative in front of the x just to make it look better. So 0 to pi minus the integral from 0 to pi, and we have negative cosine x dx, integral of negative cosine x dx. But in order to simplify this a little bit more, we can use the constant rule again. This is just a -1, right? So we can pull out the -1 outside and just make this a positive. So we can just pull out the negative right here, like that. So that's what we end up with so far, right? Now we have to evaluate from 0 to pi. So let's do this all separately, right? So let's do this separately. So let's do this separately, and let's do this entire thing separately. So first things first, we're going to be evaluating from the upper bound minus the lower bound. So it's going to be pi squared sine pi minus 0 squared sine 0. Right? Now, pi squared is just pi squared, right? Sine pi, if you look at the unit circle, right? Sine pi is supposed to be somewhere around here. This is where pi is located. And we know that sine is the y-axis, right? So sine is y, cosine is x. Sine is equal to 0 here. So we know sine of pi is just 0. So you're going to see a lot of these problems like this where you're going to have to evaluate trig functions. So you should definitely try to memorize that trigonometric tables and the unit circle and get acquainted with the unit circle, because you're just gonna have to use that when you're solving integration problems or differentiation problems. So sine of pi is 0 minus, so 0 squared is 0. Sine of 0 is negative 1. Sine of 0 is just 1, right? And that's based off the unit circle again. So all of this whole expression is just equal to 0. So what we have here, this can be, this is just 0. This entire expression is 0. So we just did that. That's 0. Now let's do this expression right here. Okay, so we're gonna do this entire thing like in one thing. So we're just gonna do the parentheses first and then multiply by 2. So we're gonna do this entire thing first and then multiply by 2. So we do upper bound minus lower bound. Then we get negative pi cosine pi minus, we have negative 0 cosine 0. So this is just going to be negative pi. So cosine pi, based off the unit circle, is negative 1. Then we have, so this entire expression right here is just 0. So it's going to be minus 0. So what we have right here is just going to be negative pi times negative 1. That's going to be pi, positive pi, right? And then we also have this integral right here. And remember, we want to make sure this integral is simpler than the previous integral we had. So this integral is a lot simpler than what we had here with the sine x and x. And the sine x and x is a lot simpler than what we had in the original function. I mean, in the original integral, where we had an x squared cosine x. So we're in the most simplest form we could be for this problem, for this integral. And that's good for us because we can just evaluate this integral of cosine x, and we know the integral of cosine x is just sine x. So we can just evaluate the integral of cosine x a lot easily once we have it all simplified. So let's actually do that. So let's pull this to the side again. So we know the integral from 0 to pi of cosine x dx is just going to be sine x evaluated from 0 to pi. You see how simple that is? We went from this entire giant expression to just a simple sine x evaluated from 0 to pi. And everything is just turning into simple answers, right? We know this entire expression is 0. We know this thing right here, this expression right here is just pi. And once we let's evaluate this as well now. So it's just going to be sine of pi minus sine of 0. Alright, so sine of pi is sine of pi is 0, right? Because I said by the unit circle right here, this is pi, and sine is 0 here. And at 0, right here, sine is also 0. So it's going to be 0 minus 0, which is just 0. So you see how easy that we're getting a bunch of zeros. So it's just making our process of finding this integral, this definite integral, a lot easier. So now we know that this entire thing is equal to 0. So let's now just put everything in one spot now, right? We know that this right here is equal to 0. So let's just put 0 there. Then we know it's being subtracted by 2 times this entire expression. So we determined that this thing right here, negative x cosine x evaluated from 0 to pi, is just pi. So let's keep this parentheses, right? Parentheses, pi right here. And this this expression right here, whatever that is, so it's pi plus this integral evaluated. So I'm gonna add addition sign, and then we said that this integral right here is basically 0, because sine pi minus sine 0 is just 0, plus 0, like that. So this is what we end up with. You see how much simpler this is from all of this? So this is just a normal simplification. This is just negative 2 pi. And our final answer is negative 2 pi. So our final answer is this right here, negative 2 pi. And what this negative 2 pi is telling us is that this function right here, x squared cosine x, has an area of negative 2 pi when negative 2 pi from the interval 0 to pi. So from 0 to pi, this function has an area of negative 2 pi. And that's basically integration by parts. And there's problems where you're going to have to do integration by parts like 5 times or 6 times. And that's basically what we have to do when we have products of different functions, especially algebraic functions. There's a way you can actually determine how many times you have to do integration by parts, and that's by the power of the algebraic function. So you see over here we had a power of 2. So we had to do integration by parts 2 separate times. But say if the power was like x to the 7th, we would have had to do integration by parts 7 times. But I feel like most professors aren't gonna go above like x squared or x cubed. That's like the max they would probably go, because if you do integration by parts 7 times, it's gonna take like very long to actually figure out the problem. So just remember that whenever you have an algebraic function times another function, look at the power of the algebraic function, and that's going to help you determine how many times you're going to have to do integration by parts. So in this case, in the case we had a power of 2, so we did integration by parts twice, and then we got our final answer. But if it was 3, we would have to do it 3 times, and so on.